All right, let's see what this has in store for us today. Advent of Code 2024, day 18. Diving right in, it's called RAM Run. You and the historians look a lot more pixelated than you remember. You're inside a computer at the North Pole. That is 2017, day 2. Okay. Just as you're about to check out your surroundings, a program runs up to you. This region of memory isn't safe. The user misunderstood what a push-down automaton is, and the algorithm is pushing whole bytes down on top of us. Run! Okay. The algorithm is fast. It's going to cause a byte to fall into your memory space once every nanosecond. Fortunately, you're faster. And by quickly scanning the algorithm, you create a list of which bytes will fall in the order that they'll land in your memory space. Your memory space is a two-dimensional grid with coordinates that range from 0 to 70, both horizontally and vertically. However, for the sake of example, suppose you're on a smaller grid with coordinates that range from 0 to 6, and the following list of incoming byte positions. Okay. Each byte position is given as XY coordinate. Oh, so I just finished doing the whole position stuff with row call. All right, well, that's fine. Where X is the distance from the left edge of your memory space, and Y is the distance from the top edge of your memory space. You and the historians are currently in the top left corner of the memory space at 0, 0, and need to reach exit in the bottom right corner at 70, 70 in your memory space, but at 6, 6 in this example. You'll need to simulate the falling bytes to plan out where it will be safe to run. For now, simulate just the first few bytes falling into your memory space. As the bytes fall into your memory space, they make that coordinate corrupted. Corrupted memory coordinates cannot be entered by you or the historians, so you'll need to plan your route carefully. You also cannot leave the boundaries of the memory space. Your only hope is to reach the exit. In the above example, if you were to draw the memory space after the first 12 bytes have fallen, using dot for safe and hash for corrupted, it would look like this. Okay. You can take steps up, down, left, or right. After just 12 bytes of corrupted locations in memory space, the shortest path from the top left corner to the exit would take 22 steps. All right. Simulate the first kilobyte falling first. Okay. Oh, this is going to be big input then, huh? All right, let's get the input. Oh, wow. 3450 lines. That's almost all of them, right? All of them would be 70 by 70, so it's 4,900. Yeah. Wow. Okay. Let's do this. This is memory. And we only care about... Oh, we're only doing the first 1024. We don't want to save everything. Let's call these the what do we want to call this? Okay, so we're going to create a list of which bytes will fall. So we'll call this a list, and we'll have it just be a vec of I64s. Simply that. Let lines equals AOC lib read lines. The input. Self list is lines iter map line. And we do, let's try it this way. Line split once on comma. Unwrap. And then we're going to map again to XY. And we'll do X at parse, unwrap, Y parse, unwrap. Collect. That should give me the full list. I should be able to print out a few of them. Like this. Self list 0 dot dot 20. I might have to put ampersand on there. Yeah. Okay. So hopefully that looks like this list here. Let's just do a tail on it and print out the last 20. Just to make sure I have, what was it? It was 3,450. So we can do 3, 4, 20, right? Dot, dot. 6836, yes, that matches. Okay, I think we have them all. We're not missing any. And now we just need to find a path, which sounds familiar. We did that a couple of days ago, or we did that for, was it day 16? Was pathfinding? We're going to use pathfinding again. Why not? It's here. It's my crutch now. So we need to simulate the first 1024 and find out the minimum number of steps to reach the exit. Okay. Let map memory equals, let's do it as a hash set of I64 is equal to self list 0. No, we could say self list iter take 1024. Oh, just collect, right? You should be able to do that. You might have to copy them. Not found in scope. Might have to say copied collect. Let's see. Yeah. Actually, we don't need to if we just put the references in here. Let's see if that works. I don't know if that'll work. Let's find out. And now we can just use A star and figure out what this prefthing prelude, right? Oh, right. We need a starting node, which is going to be, we started 0, 0, right? We started 0, 0, and we have to end at 70, 70. Okay. So we're going to start at 0, 0. That's our first argument. The second argument is a list of the successors. Okay. So we're going to say state. And now we need the directions again. Four. I know I did all of this, but this is XY. So now I'm just re-implementing everything. Let's say up. Up is this way. Right is this way. Down is this way. And then left is negative 1x and 0y. So we can generate all of the directions we want to go by saying dirs iter map dir, and we're going to create a new direction, a new location to look at. So it's state.0 plus dir.0, comma state.1 plus dir.1. That's it. That's all we need, right? And then we want to make sure that we're not going to hit something that's in memory, right? So we're going to say, as long as it doesn't, as memory does not contain pause. Now pause is, so we need to do a double reference, right? Because this is, memory is a single reference. Okay, well, we'll see if it works. The next thing we need to filter on is the position has to be on the map. So pause.0 is greater than or equal to 0, and pause.1 is greater than or equal to 0, and pause.0 is less than 70, and pause.1 is less than 70. Okay, and then we just need to collect. Right? And that gives us our vec. Right? Scoop says 7070 is a valid position. Oh, right. We're trying to reach 70. Okay. Thank you. Very good. And then, so the next one is actually the heuristic. So we can set this up as, oops, oh, I need to put a comma there. No. Am I missing something? I would have thought we would be over here. 71 minus state 0 plus 71 minus state 1. Actually, no, we still want to do 0 here because when we're on 7070, it's 0 steps to the exit. Okay. And then finally, I think that is the end state, the success state. So state is equal to 7070. Is that the whole thing? Expected ampersand unknown. Found I32, I32. Okay. So do we need to put I64 here? And then put a semicolon here? Yeah, okay, so that formats. And this should return, it was a path and a cost, and we just care about the cost. Oh, right, it's an option. It returns an option. And I see that I need to fix my contains thing there. Okay. Yeah, it returns an option path cost. Okay. So we can say if, no, we can just say let sum this, and then else like this, panic, no path found, semicolon. Consider dereferencing, okay. And then the contains thing is what? The trait borrow, blah, 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 is not implemented for that. Okay. Can I do it this way then? I can't collect. Oh, I can collect. If I tell it I want a vec. Expected. Oh, right. I have to tell it the cost. Right. So the cost for everything is just 1. That makes these, right, this 0. Okay. Now we're gonna do these double dots again. Which Rust format doesn't like. Let me widen this a little bit. 268. Oh, right. Let's get rid of this. All right, 268. Is that right? That's the right answer. Yay. Okay. Clippy. Clippy's good. Yes. Right, Scoops. Pause underscore would get rid of the double dots. All right. And that still runs and gets 268. Okay. Yeah, that's a little cleaner. I like it. Git status, git add source, git commit -m 2024 day 18 part 1. I'm wondering what part 2 is because I didn't print out the map, but it seems like it was like 80% covered based on the number of entries there are. So, okay, well, let's see what part 2 is. The historians aren't as used to moving around in this pixelated universe as you are. You're afraid they're not going to be fast enough to make it to the exit before the path is completely blocked. To determine how fast everyone needs to go, you need to determine the first byte that will cut off the path to the exit. In the above example, after byte 1 at 1 fails, there's still a path there's still a path to the exit. However, adding the very next byte at 6-1, there is no longer a path to the exit, right? It cuts off this choke point there. So in this example, the coordinates of the first byte that prevents the exit from being reachable are 6-1. Simulate more of the bytes that are about to corrupt your memory space. What are the coordinates of the first byte that will prevent the exit from being reachable from your starting position? Provide the answer as 2 integers separated by a comma with no other characters. Okay. Oops. Let's see. So what I'm going to do is here's what I did for part one is I pulled out the first 1024, which is what they asked for, and then did a search on that. But what I can do is I can parameterize this. Let's pull this out into here and call fn search self, and we'll give it a limit. And it will, instead of saying let some blah, 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 we'll just return the result of the A star search. And then, oh, this line also. And then instead of limit, instead of 1024, we'll put limit. So that means part one should be self search 1024.1. Probably unwrap.1. Oh, yeah, we just want to return that. And now, oh, that means we're returning an option of whatever A star is. So it's a vec of I64, comma usize. Oops. Oh, you're right, it's a tuple. Still not good enough? Oh, because I'm using I64s for the cost. Oh, really? So the heuristic and the cost need to match. Okay, well, we could do I64s. That's fine. I don't care. The number is small enough. Okay, so we still get 268. So we can just do brute force this, right? We can say for I in 1024 dot self list len. We're looking for the first time is none, right? So if self search blah blah blah, not 1024 I, let's call it limit. Then we're going to print out the entry that byte was AOC lib output self list limit. I probably have to say as I64 here. Otherwise it'll be unsolved. Oh, yeah. Okay. I64 can, okay, format. Oh, right. These are, okay, yeah, format. Oops. Bang. Like this. Right. Well, it's not fast. I assume that it's not stuck. Although maybe I should be printing out the, okay. So we got 6049. Took 15 seconds. That's terrible. And it's not even the right answer. Maybe I went one too far. What is it looking for? The first byte that will prevent the exit. Yeah, so the first time we get an is none, then we're done. Am I doing these backwards? Let me quit out of this. Cargo run release. Let's see if it's any faster. Okay, less than a second at least. But it still gives me the wrong answer. Input 2024, 18. 18? Yeah. Actually, let's look for 60, 49. It's at 2935. So maybe is my code bad? Because is this search wrong? If I take 1024, oh, you're right. So it would be the previous one. Somebody hit the off by one button. Okay, let's try 6411. Yeah, okay. Thanks, Scoops. But I don't like this. Here's what I'm thinking is that the data can be partitioned into can solve or can find a path and cannot find a path. Right? There's no way for us to add additional bytes. Once you don't have a path, adding more bytes won't suddenly make a path. So because it can be partitioned that way, I think what we can do is do a binary chop. So let's try doing that and seeing if that speeds things up a bit. Min equals 0. Max is equal to self list len. While max is greater than min, let mid is equal to max plus min over 2. And now we'll do a search. And instead we'll call this mid. So if we weren't able to find a path, that means we want to pull the max down, right? Max is equal to mid. Otherwise, we were able to find it, which means we have to keep moving forward, which means we have to mid minus 1. And then this is no, it could be this one. So we want to save that one. But min is going to be mid plus 1. Right? If we were able to find a path at mid, we want to check the next one up. And then inside max should be, I have to do this format thing. That's annoying. Without a space. Self list max, self list max. And then what I can do is I'll have time, right? Because we have it solved. Maybe I can make a coordinate XY thing. This should run a little bit faster. And it comes up with the wrong answer again. Max should be the first one that doesn't solve it. Yeah, I know, minus 1. But we just added, oh, I get it now. Okay. Yeah, okay. And if we run in debug mode, yeah, it's a lot faster, obviously.